Hi, I'm back. So let's start. Okay, again, feel free to ask questions because I will be going little faster now onwards. Okay, in the course. Okay, so this is what we have studied. Okay, all right. So now we have to generate control signal for add instruction. Okay, it means that we have input is of course here instruction and 2 bits that are coming here. Okay, so these are the only required information or input. Okay, within instruction also, instruction bit we need only few bits that we have seen. Okay, and then we are generating all these values. So we have to now generate these values for add instruction, and you have to tell me what will be the value of control signals. Okay, first thing is PC cell. For add instruction, you tell me what should be the value of PC cell and why. Of course, it's written here, PC cell has to be 0. Who can tell me why it is 0? Sandeep Kumar, can you tell me? Sandeep, are you there? Wow. So what Sandeep has done is that he is not using even. Sandeep, are you there? You have unmuted. Yeah, okay. This is not the right thing, bhaiya. Is your mobile not working? Don't tell me camera, mobile, microphone not working, right? Works. Very rarely, computers are so reliable that rarely fail. Just Sandeep, inform Sandeep to call me after the class. Sejal, can you inform Sandeep to call me after the class?
Okay, sir.
Okay. Atwet, you tell me.
Yes, sir. P select will be 0 because the opcode is not 63. Like opcode is not the same as that of branch or jump.
Yes, very good. Excellent. Excellent. Okay. Now next is that immediate select right here. Now immediate select has to be what? It is don't care, right? It is don't care because we don't care. We are not using this unit, right? Whatever be output here will not be used. We are taking two inputs to ALU from register file because addition of two registers, right? Okay, now here this is 1. Tell me why it is 1. Aditya,
Because in the end, we have to write the
yes, very
added
good.
value to RD.
Very good. So at the end we have to write into register. Hence it is 1. All right. Branch UN. Okay. So now we are comparing, okay, RS1 and RS2, and from BRUN we select whether it's assigned or unsigned. Okay, and we are not doing branch here. Okay, so note that this input goes to branch comparator, and we are not doing branch, so we don't care about it. So it can be anything. Okay, next is A cell and B cell. Okay, so A cell is here for this multiplexer, B cell is here. We need to select inputs that are coming from register file, right? So we select 0 for both. Okay, we don't select other inputs. One comes from PC, other comes from immediate fields. We don't select that. Okay, so we are selecting. So this is simple. ALU has to be given control signal corresponding to add. So this is add. Okay, all right. Okay, so okay, so now of course when we say add, it actually we have to give some values here, right? Some binary values. So that anyway one can code it, right? Because there's a multiple values, because there are, I think there are about 16 instructions ALU can 16 operations ALU can perform. So I guess it should be either 4 bits or maybe little higher than 4. 16, or if so more than 16, then it will be 5 or something like that. Okay, so this has to be coded. When we say add, then is for or in case we are doing multiplication, then we'll say right here mul, but actually it's coded into corresponding binary values. All right, and then we have memory write, mam or read write, right? So which is nothing but data memory. What are we doing here? We are doing 2 registers and storing the result in the third register. Are we using data memory? No. Okay, now can we say it can be anything, 0 or 1, or we don't care? No, we can't say it is anything. It can be anything. It can't be, because if it is don't care means it can be 1. If it is 1, whatever is available as address input and whatever junk is available as data input will be returned. So we have to specifically say this has to be 0. It means that we are not using it. So it means that reading can be done, output can be available, we don't use it, but writing is not allowed. Otherwise something erroneous get written here. Okay, and next is WB cell, write back cell, right? So now we have to select what? We don't have to select coming from memory. We have to select, and this is PC plus 4. We have to select something which is wow, what is it? Okay, so we'll have to basically select ALU out. So WB cell ALU out is this one. So what is PC plus 4 should be then this one. Anyway, the one which is coming from ALU is to be selected. Okay, so we in this case is the ALU cell is equal to 2, but we can see it how it is, like earlier. Here it is okay, all right. So the one which is coming from ALU is here, right? So it's a 2. Okay, fine. So now we have generated all control signals. These are the input signals shown as green, which is corresponding to code, some bits corresponding to add instruction, and then something coming from comparator. There are 2 bits coming from comparator BREQ and BRLT, and these are the output shown from orange, in orange color, right? So these are output, and we have seen for add instruction PC is equal to PC plus 4, A cell something that's coming from register file, B cell something from register file, ALU select is add, mem read write is read, and register write has to be 1, and WB select has to select something coming from ALU. Okay, and now out of this here add, we know we can just manage with basically how many bits here, what it shows, uh, the bits here that's shown, which is 5 plus 3 8 plus 1 9 bits are sufficient for us to differentiate between different instructions. Okay, so now we have this table available. Okay, for each instruction we can code this. All right. So for example, difference between add and subtract is that everything will remain same. Only ALU select here in the first case add, second case subtract. Okay, so this table one can easily draw. Any question?
In case of branch instruction,
Mhm.
like if branching is not taking place, then we'll have to increment PC rate. But how will we do that? Because we are connecting that line, which is the output, directly to that multiplexer, and we are selecting the bottom one of the multiplexer.
Shall we go to previous diagram?
Yes,
Okay. Okay, let's go here, right?
yes, in this.
Okay, what we have shown here is for add instruction, not for branch. Okay, branch, what happens is that this ALU, branch target address has to be calculated. Okay, so target address is what? How do we calculate the target address in case of branch instruction?
So we'll add immediate to that thing.
Yeah, so we do some operation. Okay, basically we take PC value. Okay, we take
Yes.
PC value here. Okay, and after selection this comes here, and offset value comes from, okay, there is a little mess here. Offset value will come here, and addition of that is branch. Basically,
Yes,
okay, so this comes here. Oh, sorry, it will, well, this diagram is little messy, but it will come to come here. Some
sir,
of,
in case of all branch instructions, we will select the PC select will keep it as 0, right?
yeah, yeah,
Sir,
PC select will be for all branch instruction and jump instruction, it will be 1, which is corresponding to upper input. You can define what is 0 and 1, but it's basically something that's coming from ALU will be selected.
sir, but if branching is not taking place,
And
then
bottom one.
actually we'll have to
Uh-huh.
increment +4, right? But
Yes.
in that case, how will we do that? Because we are always keeping this as the upper one
No,
in case of branch.
no. In case of branch, we have to see the values BREQ, or these 2 bits. So if these are enabled, it means that
Yes,
if the values are same and branch conditions are met, only then, and looking at some bits from here corresponding to branch instruction, uh,
yes,
this decision is to be taken. Okay, so you can see that same thing is reflected here. Uh, just a minute. Oh, okay, here. So we have taken BREQ. These are 2 values we have taken. When branch equal to BR equal to 0,
yes,
it means that conditions are not met. If the 2 register values are different. Then
yes,
PC is equal to PC plus 4. The bottom one is to be taken. Okay, if it is 1, BR equal to is 1, it means that both registers are same, then output from ALU is to be considered. That's shown here.
yes, sir. But when we did that OR gate, sir, like for that, when we
Yeah.
compare that with this thing, we just considered the opcode for branch and JL and JLR. But we'll have to also, right?
No, so you have to see that what are we doing here, there, right? So for example, let's go back. Uh, this is for branch, right?
Yeah.
Okay, so this one is for this is for branch. This is for, one is for JL, another for JLR. I don't know what is what, right? So now if we can see the opcode for all branch instruction is 63.
Yes.
Okay.
Uh, yes. So
Okay.
if
So all right. So okay. So you mean to say is that now we have to okay.
to take that branch equal to, we'll have to see that also, right? Like
Yes,
if they
yes,
are equal or not.
yes. You are right. You are right. You are right. So we have to also see that. Whether
Yes, that will also be.
yeah, that is also Buddhism. It's not shown here. You're right.
Yes.
Yeah, all right. Yeah, you very good, very good. So that will come in the design, overall design.
Yes.
You're right. Absolutely right. Okay, so based now we can create this kind of table, and based on that we can design the control logic. Okay. Now there are two ways we can design this. All right. First is that, see, whole idea is that now it's getting certain inputs, which is few bits from instruction and BR and EQ. Okay. So basically, we are taking 9 bits plus 2 bits. These are all input and we are generating this. So now we can do it two ways. First is we can create a combinational logic circuit, FSM, whose inputs are these and output is all this, right? And second is that we can consider these as a memory address, okay, and out that will store these control signals. Okay, and it means that just read that location and it will generate signals corresponding to what uh, the instruction is meant for. Okay, we'll see that. So first is hardwired, this hardwired, which is using FSM, and second is using memory, ROM. Okay, and this is simple. Okay, however, this is faster, simple and flexible. Okay, so we are using two methods, which is ROM, which is the second one here. Okay, sorry, micro programmed. So this is micro programmed, and then the conventional logic circuit here, right? So both are being used. This has been popular, but if you want to create a machine which is very fast, then we use combinational logic circuit. And nowadays it's very simple to design this, right? But it's little more expensive. The first method is which is micro program. Note that this word in interviews very often is used microprogramming. Okay, it's nothing but generation of control signals using memory method, right? Or basically we treat this as a small program. So what we do here is that these are the 11-bit inputs. We have seen 9 bits are coming from instruction and these 2 bits. And then we read a location or corresponding to that instruction, these bits or corresponding to instruction, and this output is generated. Okay, so this kind of design you can easily do, right? So these are 15 data bits. So this is the output. And very simple way of doing this is as follows, right? So these 11 bits, you use an address decoder, and each will decode corresponding to an instruction. Okay, you go and read that word. For example, a word corresponding to the location here. Okay, and then this will give all these signals for add. It basically bit pattern is stored there, as simple as that, in that location, and which will output. Okay, so you can let's look at it now for simple instruction. So let's look at this add and subtract instruction. Okay, now you look at these bits. Okay, now can you say for add what should be the control signal based on these 9 bits? Okay, so again this is the same thing that we have shown earlier. So now we'll take this and now try to code this for corresponding to each instruction, right? So let's look at this bit, RW register write enable bit, and now create a circuit for this, right? So now we store control word corresponding to add. So we can use add and or logic, and then look at these bits and 2 bits here, and then we can do add is equal to, say this is 30th bit and is 0, so that bit bar and then end with 14th bit, which is bit here, which is again 0 bar, and so on and so forth. Fifth bit must be 1, and so on, right? So similarly, we can do it for subtract. Okay, and then we can say this is nothing but add plus subtract plus what other values which give bit which is used in register, which can give register enabled input as one. Okay, so in this way we can generate control signals. Note that there are two ways to generate control signals. I mean, we can either use this method of ROM based controller, which is very simple. Only thing is we need a decoder, and from decode we select one output here, and that output is actually gives you control word, which you take it out, as simple as that. And in order to create, we can actually create this by using FSM as well. All right, so this simply shows one simple step. Okay, any question?
So
Mm-hmm.
till now we have been thinking of control unit like an FSM, right?
Mm-hmm.
But now we are looking at ROM. But in an FSM, the output depends on input as well as the current state, right? So how that is interchangeable with the ROM, where you just input the values and that behaves like an address. So it is just dependent on input, right? So
Yeah, so okay, good question. So what exactly, I mean, when you see uh, I mean, do we here at this point, till the point we have, till what we have studied, is any instruction dependent on previous instruction?
no, sir.
So we can do it then, right? Because FSM may not have a feedback loop. I mean, it can be just simple control, combination logic circuit.
Okay, sir. So we just need combination logic. Like FSM is not necessary.
Yeah, yeah. I mean, of course, I mean, we may not need truly FSM for something that we have designed so far.
Okay, sir.